Section 15.4, thermal processes. So now we're going to get into applying that first law of thermodynamics to some specific types of scenarios that we'll see. First off, I'm going to mention that all of these processes are quasi-static processes. That just means that it occurs just slowly enough that there's a uniform temperature and pressure throughout all regions of the system at all times. So there isn't a change at one part that hasn't reached the other part. We assume it's all staying at thermal equilibrium and the same pressure throughout, even as that pressure might be changing and the temperature might be changing. All right, so that's the type of process we're looking at here. And we'll see that there are 4 processes in particular that we want to look at. And all of them have something special about them, something that if you notice that it's this type of process, the calculation often becomes simpler in some way. So here's the list of them. Isobaric means it's constant pressure. The iso meaning constant, and bar, you can think of that actually used to be a unit of pressure is bar. So isobaric, constant pressure. The pressure is not changing. Isochoric is constant volume. The core, I think, is another Latin root referring to volume. Isothermal is one that's a little easier to follow directly. Thermal meaning temperature, so it's a constant temperature process. That as the process is happening, the temperature is staying at one value. And then the final process here is the adiabatic process. And this one doesn't hold constant pressure, volume, or temperature, but there's no heat transfer. So often with adiabatic, it occurs in something that is well insulated, or it occurs quickly enough that there isn't time for heat to go in or out of it. All right, so that's the brief overview. Now we're going to take a closer look at the isobaric and isochoric to get us started. Now, in order to look at these thermal processes, I mentioned we care about the first law, that the change in internal energy is Q minus W. That means we're going to need a way to figure out the work, right? So that we can better understand how the first law works. So if we think back to work, way back in chapter 6, we saw that work was force times displacement, F times S. So I wrote that here in the slides, F times delta S. I added a delta just to emphasize that that is a displacement, a change in position. We can also then pull in our understanding of pressure, though, and note that pressure was force divided by area, or you could write that the force is the pressure times the area. So if you fill that in for the force, then we have pressure times the area times the displacement, delta S. But the area times the delta S, that's just going to be the volume, right? The cross-sectional area times how much it moves. That's what's depicted in this picture. Is one example, for instance, we have a piston that moves up, so it moves through some displacement, delta S, and then the cross-sectional area is the size of that piston, and I'll tell you how much the volume is changing. So that's our volume, and then we have pressure, and there's some overall change if we want a general work formula. We know the volume has to change, the pressure might change too, it turns out. But our isobaric process is one that occurs at a constant pressure. So if it's a constant pressure, we can pull the pressure outside of the delta, and we can calculate the work for an isobaric process with pressure times the change in volume, which you could write as P delta V, or P times V final minus V initial. And it is, again, a final minus an initial in this instance, in that we will get positive work if it expands, and we'll get negative work if instead the system is compressing. All right, and this figure here actually demonstrates an example of setup that would produce an isobaric process. So we have a fluid inside here. It may even be water, liquid, and there's a piston on top that's just resting on top of the fluid. There's some mass on top of that, and the weight of that piston is holding it in place, but the fluid's pressure is pushing back on it and exerting a force on it, which is supporting the piston so that the piston doesn't fall. But if we add a Bunsen burner below our fluid, then that's going to add heat and increase the temperature. So if we think back to our ideal gas law, PV equals nRT, which is helpful for thinking, even if this is a liquid and not a gas, that, hey, if our temperature increases and the amount of the fluid stays the same, something over here is going to need to increase. Well, the pressure, it turns out, is just set by how much weight we have on that movable piston. If we put more weight on the movable piston, that will increase the pressure, right? If we take weight off of the piston, then it'll expand and less pressure will be needed. But the piston with the weight on it is actually creating the pressure in this scenario. So as long as we're not changing the weight on the piston, the pressure will stay the same. So the only thing left to change is our volume will need to increase if our temperature increases. We could, in theory, if the pressure wasn't held constant, we could have both of these increase. But here we know the pressure is held constant, so the volume increases. And that's what's shown here, right? The piston moves upward, and the final volume is now greater than the initial volume. This is positive work done by the system. So this is one way that you can think about an isobaric process. And this is a pretty quick equation to calculate the work done. You just need to know the pressure that stays constant times the change in volume. Another way you can think about calculating this work that we'll see is actually a general result is if we take that same equation for work equals P times delta V, and we can construct something known as a pressure volume graph, or it's sometimes abbreviated as a PV. So PV graph, PV diagram, those are all terms used to describe this. What this is it's just a graph with pressure on the vertical scale and volume on the horizontal scale. That's where we get PV. And we can plot out particular points. Like here is the initial point. So this is our starting point. And the system has some pressure and some volume. So we can plot that point based upon those values. For an isobaric process, we know that as the process occurs, the pressure stays constant. And so we could then fill in that it stays at this constant pressure at the final point. It still has the same pressure value, right? We haven't changed on the vertical scale, but the horizontal scale, our volume has increased. So this is a good depiction of the process. And we note that if we compare this to our work equation, it's the pressure, which is a constant value, and that could be shown as the vertical part of this, right? It's just the pressure times the change in volume. So our V final minus V initial. Notice V final minus V initial is the length of this side of the rectangle. So VF minus VI. So if we're multiplying the pressure times the change in volume, that's just finding the area of this particular shape. And this, it turns out, works for isobaric processes, but it's also a general result that the area under a pressure volume graph is the work for any kind of process. So this is a really handy thing to keep in mind, and it's one of the reasons why PV graphs are so useful to us, is if we can calculate the area under the curve for the process, then we will know the amount of work that was done. All right. So now that we've seen the isobaric process, let's take a look at an example. So example 3, isobaric expansion of water. It says 1 gram of water is placed in the cylinder and the pressure is maintained at 2.0 times 10 to the 5th pascals. The temperature of the water is raised by 31 degrees Celsius. The water is in the liquid phase and expands by the small amount of 1.0 times 10 to the minus 8 cubic meters. Find the net work done and the change in internal energy. Right. So there are some key clues here. The important thing in this problem that's mentioned, and this is something you're going to have to look at when you're solving problems, it says the pressure is maintained. Because it says the pressure is maintained, that means our pressure is constant throughout the process. That tells us, without even the heading, that this must be an isobaric process. So that's a really key detail, something you're going to want to clue in on. So we have the pressure. We also have this 31 degrees Celsius. What is that? Well, notice it says that's the temperature of the water is raised by that amount. So that sounds like our change in temperature, right? So that's good. So delta T is 31 degrees Celsius. Water is in the liquid phase. So here we see that these thermal processes do apply to liquids, even though we'll commonly be looking at gases. It still holds for liquids too, and expands by the small amount of this 1.0 times 10 to the minus 8 cubic meters. Cubic meters, what are the units of that? Those are the units of volume, great, and it's expanding by this amount. So is this our initial volume, final volume? It's neither the initial or the final, it's the difference, right? This is the amount that we have expanded. So I'd write this as my delta V. Is that number. All right, so we want to find the work done, capital W, and the change in internal energy, which we remember is delta U. So that's good to identify those variables. That will help us as we're thinking about equations. Well, since we noticed it was an isobaric process, solving for the work is very quick, right? We know that the work is that constant pressure times the change in volume. Boom, part A. We're set to go for it. What about the change in internal energy? Well, the fact that we solved for the work already gives us a clue that we could probably use that again. So change in internal energy, we could use maybe our first law, that the change in internal energy is Q minus W. That's a good equation. We already know the work. What about Q? Does it tell us the heat? Notice it doesn't directly tell us the heat here. It does give us the change in temperature. So if our liquid water is changing temperature, how much heat is going into it? Well, that's where we can pull in our ideas from way back in chapter 12, right? We had an equation for the heat as something was changing temperature, right? We had Q equals ml for if something was changing phase. If it was changing temperature, remember we had Q is equal to mc delta T. And so we have that change in temperature, the specific heat of the water, we could look that up. What about the mass? Oh, there's a piece of information I missed, right? It mentions 1 gram of water. There we have our mass, at least in grams. We will want to convert this to kilograms, right? Remember, 1 gram is going to need to move that decimal place over by 3 to make it kilograms. 1, 2, 3. And so that becomes 0.001 kilograms. But now we're in good shape that we can solve for the heat here. And then we can plug that into our first law, and we'll get our change in internal energy. So let's take a look at bringing this all together. All right, so work is equal to pressure times the change in volume. So we take those two numbers and multiply them and come out to 0.0020 joules. Now, how did we get to joules? I mean, I like getting there. It's a good result, right? So we have pascals times cubic meters. It's kind of funny, but remember pascals is pressure, so that's force over area. So we could rewrite this as force per square meter times cubic meters. And then we notice that most of these meters are going to cancel out, and we'll just be left with force times meters, which, oh, sorry, force, I should have an N there. I tend to think in terms of force, but this should be a Newton. That is our proper unit of force. All right, so newtons times meters, when those multiply together, they indeed give us the unit of joules. So it does work out, promise. Pressure times volume does still give us our favorite unit, joules. So we do have that. All right, then we have our first law, change in internal energy is Q minus W. To calculate Q, we come back to that mc delta T. So we have the mass times the specific heat capacity of water, 4,186 joules per kilogram per Celsius degree, times 31 Celsius degrees, comes out to 130 joules. So 130 joules minus 0.0020 joules comes out to, in the end, 130 joules. So it turns out this amount of work was actually pretty tiny because the change in volume was tiny. And the amount of work done really depends on that volume. Because it turns out anytime we look at a process, a thermal process, there must be a change in volume for work to be done. So to highlight this, we could look at isochoric processes. Isochoric processes are ones at constant volume. So you could imagine just having a closed cylinder. It's capped, it can't move, the volume can't change. So even if you heat it, then the volume's fixed. The pressure can change, but that's about it. So on our pressure volume diagram, right, all that can change is the pressure could go up as you add heat, but the volume stays the same. What's the area under this curve? The area under the curve is 0. So for a constant volume process, the work must also be 0. Because the work is 0 based on our first law, the change in internal energy is just going to be equal to the heat for this isochoric process. So if you identify that something has a fixed volume, that's another really useful thing on problems. All right, one more type of problem-solving technique that you can use is work in an area under a pressure volume graph. So determine the work for the process in which the pressure, volume, and temperature of a gas are changed along the straight line in the figure. So this isn't any of our special processes, but we can still get the work done, remembering this idea that the area under a pressure volume graph is the work for any kind of process. So notice in this pressure volume graph, they give us, for each of these squares, they give us how much volume change that corresponds to. That's sort of our delta V. And then how much pressure change each box corresponds to, which could be our change in pressure, delta P. So all we have to do is count the number of boxes that we have. So let's see, 1, 2, 3, 4, 5, 6, 7. And then it starts to get a little hard, but noticing that there are these extra little triangles here, those could probably fill in. So I would say we could even count these last ones as 8 and 9, that we have 9 boxes. Once we know we have 9 boxes, then we can just take that number of 9 and multiply it times the area of one box, and that will give us the total work under the curve. So looking at this graph, work, since the volume increases, the work is positive. Notice if it was going the other way, we would actually have a negative work, so that'd be something we would need to take into account. But we can estimate there are 9 colored squares in the drawing, as we did, and then the work is 9 times the area of one of those squares. So the 2.0 times 10 to the 5th pascals times 1.0 times 10 to the minus 4th cubic meters. Now if you multiply that out, it comes out to 180, once again, joules, and it again is positive because the volume has increased, because it has expanded. We would have to add in a negative sign if instead the system had been compressed. So this introduces the idea of thermal processes, and we will continue in the next section taking a look at thermal processes specific to an ideal gas. So more to come, stick around.